In the PDP-11 system, negative numbers are written in 2's complement notation. Therefore, we can detect negative numbers simply by looking at bit position 15, which is the most significant bit. A 0 in the most significant bit indicates a positive number. A 1 indicates a negative number. The remaining bits in the word represent the magnitude of that number. At this point, let's briefly review positive and negative numbers. Changing a +5 to a -5 is a simple procedure. Notice the binary equivalent of +5. A 0 in bit position 15 indicates the number 000101 is positive. Converting this +5 to a -5 takes 2 steps. First, we complement the entire number, including bit 15. When a number is complemented, all zeros are changed to ones, and all ones are changed to zeros. The second step is to add 1, or to increment, the number. This complementing and incrementing process provides the 2's complement form of the number. Although the binary value appears to be 73, it is actually -5. In other words, if the number starts with a 1, it is interpreted as a negative number, written in 2's complement form. In this example, 73 is the 2's complement of 5. Therefore, our number is now -5. To summarize, changing a plus to a minus value is accomplished by complementing and adding 1 to the entire word. An identical procedure is used to change a minus value to a plus value. Again, we complement and add 1 to the entire number. In this case, however, notice that the binary equivalent of -5 is in the 2's complement form. In order to complement a number, we change any 0 to a 1 and any 1 to a 0. In the PDP-11, we have a single operand instruction called complement to do this job. Thus, to generate negative numbers, we simply take the positive value and use the complement and increment instructions to convert it to the equivalent negative number. Or, we can do it even more simply by using the single instruction negate. Negate is another one of the single operand instructions in the PDP-11 instruction set. So far, we've talked about 5 single operand instructions: clear, complement, increment, decrement, and negate. We've also reviewed positive and negative numbers. Let's take some of these single operand instructions, combine them with the loop and tally techniques mentioned earlier, as well as the addressing modes covered in the previous unit, and use all of these tools to solve a particular problem. Suppose our problem is to clear out the entire memory, no matter how large it is. We'd like to do this as efficiently as possible. If we want an efficient program, the instruction must be combined with the addressing mode that will give it the most power. Here, a clear instruction is used with the auto-increment addressing mode. We'll get back to this instruction in a moment. The first step in clearing out the entire memory is to make a pointer. R1 is loaded with a 0 so that it points to the very first location in memory. The second step is to load the instruction. In this case, we're using the clear instruction in the auto-increment mode. This instruction will clear the contents of a location specified by our pointer, which is R1, and then move the pointer to the next location. Notice that we're loading the instruction itself into the next to the last memory location. The reason for this will become more apparent as we step through this example. Our third and final step is to make a loop so that the program continues running until the entire memory has been cleared. We load a branch -2 instruction into the very last memory location. This instruction causes a branch back to the clear instruction. We can now load the address of the clear instruction into our PC and start this 2-instruction program. When the program starts, it first clears the contents of the location specified by the pointer. In this case, the very first location, 0, is cleared. The plus sign after the instruction indicates the auto-increment mode. Therefore, once the location has been cleared, the pointer is incremented automatically to the next memory location, which in this case is location 2. The program now executes the branch -2 instruction, which simply returns us to the clear instruction. In effect, the program loops so that the process is repeated. These 2 instructions will cause the program to keep looping.
Each time the program runs through the loop, a memory location is cleared. The pointer moves to the next location, and the program branches back to do it again. Notice that as the program continues looping, it keeps moving down through the memory, clearing out locations sequentially. What happens once all but the last two memory locations have been cleared? The instruction must clear the location specified by the pointer. However, the pointer is now pointing to the instruction itself. So what will happen? The program actually clears out the instruction, then increments the pointer, which then points to the branch -2 instruction. This instruction causes a branch back to the previous word in memory. But there is no instruction there anymore. It was cleared just a moment ago. All zeros is the opcode for a halt instruction. Therefore, the program stops at this point, having cleared out every location in memory except for the very last one. This last location can be cleared out by using the console switches. There are more single operand instructions. You already know about 5: clear, complement, increment, decrement, and negate. We'd like to discuss 6 more. Let's start out by talking about multiplication and division.
When multiplying any decimal number by 10 or a multiple of 10, it's simply a matter of shifting the decimal point. For example, if we were multiplying 62 by 10, we simply shift the number over one place to find the answer, which is 620. Multiplying by 2 in the PDP-11 computer is essentially the same procedure. We shift one or more places to the left. For instance, multiplying octal 12 by 2 is accomplished by shifting the bits one place to the left. This provides the answer, octal 24. Notice that a 0 is loaded into the word to fill the bit position that was vacated as the word is shifted left.
Multiplying by 2 to the 3rd power is accomplished by shifting 3 places to the left. Here the effect is similar to decimal because 3 places indicate one octal digit. The 3 shifts have converted the number 062 to 620. Again, notice the zeros that are shifted in from the right.
Dividing by 2 is similar to multiplying by 2, except that the shift is made to the right rather than to the left. Here the octal number 62 is shifted one place to the right to convert it to the octal number 31. Again, notice that zeros are shifted into the word as needed. Also notice that the bits shifted out of the word are lost.
A shift left, or multiply by a power of 2, is performed by the single operand instruction ASL, or arithmetic shift left. A shift right, or divide by a power of 2, is accomplished by ASR, arithmetic shift right. This is a small program for multiplying by 32, which is the same as 2 raised to the 5th power. Suppose we want to multiply the number 16 by 2 raised to the 5th. The number to be multiplied, in this case 16, is loaded into register R1. An ASL, or arithmetic shift left instruction, is used for each multiplication by a power of 2. Thus, after the second instruction is executed, the number has effectively been multiplied by 2 raised to the 2nd power. After the program has stepped through all 5 shift instructions, the number has been multiplied by 2 raised to the 5th power, and the program stops. Can we reduce the number of instructions required to perform this multiplication? Yes, there is a simpler approach using the looping technique. As before, the number to be multiplied is placed in R1. In this case, however, we load R2 with a multiplier expressed in powers of 2. Multiplying by 32 is the same thing as multiplying by 2 raised to the 5th power, so we load a 5 into R2. The first instruction, ASLR1, multiplies the number by a power of 2. R2 is then decremented to keep track of the number of multiplications. It is, in effect, a counter. If the count is not 0, the program branches back and goes through the process again. After the program has looped 5 times or has multiplied a number by 2 to the 5th, the counter will be at 0 and the program will stop. Although the shift instructions ASL and ASR are very useful, they do have one disadvantage. As we shift left, for instance, we keep adding zeros to the number. However, the bits shifted out of the word are lost completely. Suppose we didn't want to lose these bits. What could we do? One solution would be to construct a circular buffer so that a bit shifted out of the left side of the word would rotate around and enter the right side of the word. Thus, we would continually shift the bits without ever losing a single one. The ROL, or rotate left instruction, does just that. Rotate left is another single operand instruction. Notice that in constructing the circular buffer, the C bit of the PSW is used as a link between bits 15 and bit 0 of the data word. When the rotate is executed, the value in bit 15 moves into the C bit, and the former contents of the C bit moves into the 0-bit position. We can therefore rotate the entire word one place to the left without losing any information. There is also an ROR, or rotate right instruction, which is identical to the rotate left, except that the bits are rotated in the opposite direction. In this case, the bits are rotated from the 0 bit to the C bit and from the C bit to bit 15. Rotate instructions can also be used with bytes, just as any single operand instruction can be used with a byte. The rotate instruction, ROLB and RORB, function in an identical manner as before, the C bit forming a link between the highest and lowest bit in the selected byte. Here you see operation of a rotate left instruction on an odd byte. Bit 15 rotates into the C bit, while the C bit rotates into bit 8. Notice that the assembler mnemonic for this instruction is ROLB. We've covered quite a bit so far, 5 different single operand instructions, plus operation of the 2 shift and 2 rotate instructions. That makes 9 single operand instructions. How many more are there? There are only 2 more single operand instructions that we will discuss. The first is the swap bytes, or SWAB, instruction. Remember the high and low bytes that comprise any PDP-11 word?
Well, the swab instruction simply reverses these bytes so that the low byte moves into the high byte position and vice versa. What could be more simple? Test is the last single operand instruction we're going to discuss. This instruction simply tests the operand to determine if it is either a minus or a 0. The opcode for this test instruction is TST. Hence, TST tests the operand and, depending on the operand's value, either sets the N bit or the Z bit.
That finishes our discussion of single operand instructions. You've used the clear, complement, increment, decrement, and negate instructions. We've also talked about the arithmetic shift left and right instructions, as well as rotate left and right. And finally, we covered the swab and test instructions. You've probably noticed the instruction card we gave you along with the workbook. All of the single operand instructions we've discussed are listed on this card. We'd like to take just a moment to explain the format used on this card. The black square on the instruction card indicates that this particular bit, bit 15, may be either a 1 or a 0. In other words, you have the option of selecting a word or byte operation. The next 3 octal digits indicate the opcode for the specific instruction. In this case, the code 050 always is used for a clear instruction. Notice the 2 Ds following the opcode. These indicate the 2 portions of the destination field, the addressing mode and the selected general purpose register. The DD is printed on the card to indicate that you have the option of using any addressing mode with any register you so desire. Finally, there's a mnemonic of the instruction itself, which is used in the assembler. In this case, CLR specifies a clear instruction. Notice that it's followed by a B in parentheses. When using a word instruction, type only CLR. On the other hand, when using a byte instruction, type the mnemonic CLRB. However, don't use the parentheses. It's time now to open your workbooks and study the single operand instructions. Please do as many of the workbook exercises as you possibly can. Only by using these instructions as much as possible will you be able to thoroughly understand them. Please do not begin any new material until you have finished the exercises and check your responses against the answers that are included in the workbook. When you hear the next tone, turn off this playback unit and proceed to the workbook exercises. After you've completed these exercises, you can continue with this study unit.